Good morning, everyone. My name is Pranav, and I am from Institute of Aeronautical Engineering (IARE). Today, we are going to discuss about one of the most interesting topics: Taylor series expansion for non-linear displacement relationships in mechanical linkages. So, coming to the introduction, mechanical linkages such as springs, beams, joints, and robotic mechanisms often show non-linear force displacement behavior. It is hard to analyze directly because equations are complex. Taylor series helps us to approximate nonlinear force displacement relationship with similar polynomial expressions. Coming to what is nonlinear force displacement relationship. In many mechanism systems, especially in linkages, the relationship between the applied force and the resulting displacement is not always straight or proportional. In simple words, when we apply a force, the output displacement does not increase in a uniform or linear manner. This happens because mechanical linkages often involve geometry dependent motion and also material nonlinearity, change in angle, elastic deformation, or complex interaction between elements. A nonlinear force displacement relationship means the response curve is curved and the stiffness of the system changes at different positions. Such nonlinear behavior is very common in mechanisms like springs, levers, compliant mechanisms, and robotic joints. Understanding this nonlinearity is essential because it directly affects accuracy, stability, and the performance of the mechanism. For example, f of x equal to kx plus x square and f of x equal to a power bx. Coming to why is Taylor series, the main reason we use Taylor series in such mechanical systems is because non-linear relationships are usually difficult to analyze directly. They cannot be solved using simple algebra, so we approximate them. The Taylor series provides a systematic mathematical technique to expand a complex nonlinear function into an infinite polynomial series around a chosen operating point. By doing this, we convert a difficult nonlinear expression into a combination of simpler terms that are easier to evaluate. Engineers commonly use this to approach the steady changes and predict behavior near the reference point and linearize a system. Also, the stability analysis. Uh, the Taylor series allows us to capture their essential behavior with manageable equations. And the Taylor series formula is f of x equal to f of x naught plus f dash of x naught into x minus x naught into f of f dash dash of x naught into x minus x naught plus f dash dash x naught by 2 factorial into x minus x naught whole square plus f dash dash of x minus x naught by 3 factorial. This formula represents the function as a sum of derivatives of different orders evaluated at the expansion point. Each term added increases the accuracy of the approximation. In the context of mechanical linkages, the force is usually written as f of x, where x is displacement, and we expand f of x around point where the system operates. This gives us the polynomial representation of nonlinear force curve, allowing us to calculate approximate values without solving the full complex model. Coming to the linearization using Taylor series, linearization is the process of simplifying a nonlinear equation into its closest linear form near a chosen point. When the nonlinear relationship is mild or where the displacement range, range is small, the first order term of the Taylor series is often sufficient. In this case, the force displacement relationship becomes f of x equal to f of a plus f dash of a into x minus a. This represents the straight line approximation that is valid in a small region around x equal to a. Engineers use this linearization for quick calculations, designing controllers, or predicting system behavior under the small contributions. Although it is the simplification, it provides valuable insights that allow us to analyze mechanism without dealing with full normality. Now, coming to the first example, in the first linkage, the focus is understanding how geometry leads to nonlinear behavior. As the linkage rotates, the angle between numbers change, and also the relationship between the input force and output displacement does not remain constant. By applying Taylor series about a known configuration, typically the equilibrium or rest position, we can express the force as a polynomial that reflects these geometric variations. This allows engineers to predict how linkage will behave. Coming to the second one, the nonlinearity arises due to the elastic deformation in this. Here we have like f of x equal to a e power bx and expand a x not equal to 0. Oh, as the linkage bends or stretches, the restoring force becomes nonlinear using Taylor expansion. The nonlinear stiffness can be approximated by including higher order terms such as second derivative, which represents curvature or nonlinearity intensity. This enables engineers to calculate forces more accurately, especially when the deformation is not small. These approximations are very useful in complement mechanics and flexible joints where material properties are significantly influence the force displacement profile, where e power bx is equal to 1 plus bx plus b square x square plus 2 factorial plus b cube x cube by 3 factorial plus so on. Coming to the general form of the force in leakage, it's like non-linear force displacement arises from geometry, material behavior, and also contact and joint characters. Like you can say the general form of the force is the expand in a mechanical linkage can be expressed as the function of displacement, geometry, and the material properties. Usually, it is represented as f of x, where x is the displacement. This function may involve trigonometric expressions, stiffness coefficients, and geometric parameters. Since these expressions can become very complicated, directly computing f of x for position is often impractical. Therefore, engineers expand f of x using the Taylor series so that the overall force can be expressed as the sum of constant linear and non-linear components. This makes analytical and numerical calculations significantly more manageable. And coming to its general form, it's like trigonometric. This may include in trigonometric terms, exponential stiffness, high order polynomial terms, coupling between the multiple joints, Taylor expansion, allowing the each one to uh, calculate analytical calculation significantly more manageable about an operating point. And understanding the expansion point is like choosing the correct expansion point is crucial for achieving an accurate Taylor series approximation. Typically, the expansion is performed around an equilibrium position in an initial configuration or a point where the system operates most of the time. The closer the actual displacement stays, the chosen point be the most accurate the approximation becomes. If the displacement moves far away from the expansion point, higher order terms must be included to maintain accuracy. Therefore, the selection of the expansion point directly influences the quality of linearization and overall prediction. Coming to the accuracy considerations, accuracy in Taylor series approximation depends on the number of terms retained by the nonlinear system. Also, the amount of displacement, like including second or third order terms, captures curvature and bending more effectively, improving precision. However, each additional term increases the complexity. So engineers must balance simplicity with accuracy depending on the purpose of the analysis. In many real-world designs, a second-order approximation provides a good compromise for mechanical linkages. Also, the rules like for every small displacement one, for moderate displacement, they required high. For large displacement, they required low. In this way. Coming to the limitations, they are accurately only near expansion point. Although the Taylor series is very powerful, the approximation is only readable near the expansion point. If the displacement becomes too large, the polynomial may no longer match the actual behavior. Highly nonlinear systems might require many high order terms, making method less convenient. Additionally, the Taylor series relies on the existence of continuous derivatives, which may not be available for mechanisms with sudden geometric changes or discontinuous. Therefore, engineers must understand when Taylor expansion is suitable and when a full nonlinear analysis is necessary. Coming to the conclusion, Taylor series expansion is a powerful tool to approximate nonlinear force displacement relationships in mechanical linkages. It allows engineers to linearize complex systems for analysis, design, and control, especially near an operating point. Using the first order linear term, we can analyze, predict, understand the behavior of the uh, mechanical linkages with much greater simplicity. Although the methods has limitations, it remains a widely used tool in mechanical engineering, robotics, and structural analysis due to its balance between accuracy and analytical convenience. Thank you.